day, everybody, and welcome to this WSI webinar hosted by me, Lars Vatsgård, Head of Development at WSI. With me today, we have Håkan Nordgren, who is our CTO and Chief Architect, who will be presenting this webinar. Also running the technical stuff, we have our, normally he's at the helm of his Linux rig and developing software, but he's also doubling up as handling the technology for our webinars. Thank you, Hamid, for that. So having that said, I hope all of you hear us nice and well, and I will hand over the word to you, Håkan.
Thank you, Lars. So, hello everyone, Håkan Nordgren, CTO and Chief Architect at WSI. What we will go through today is a low power IT design, which is a part one of a series of seminars. Low power design is extremely complex and it's not possible to go in one webinar into all the bits and details, of course. So we will cover system, hardware and software aspects today, and we will also end with a case study. I think that will be very useful for you. When we start this, I would like to dwell on a sentence that I get in different flavors over and over again, and I have received this for many, many years. This is when you discuss the power consumption of something in a design, and you might come with the conclusion that this consumes quite much power. And you get back into your face, well, this power consumption is nothing. It's negligible compared to the cellular modem or to the whatever modem or whatever device that is. And this is not true in itself. It might be true, but it's not true in itself. And I would like to just clarify my ideas regarding this. Everything when it comes to really low power is about duty cycle. And the duty cycle of the function X and the duty cycle of the modem itself, in this case, is the one that will judge whether this sentence is true or not. If you have a modem that is continuously running, yes, that will consume much more power than function X probably. But if the modem is used only once per 24 hours, you connect, send a byte of data, and then you disconnect again, while function X is continuously running, that function X will actually be the dominating power consumer in the system. So this is extremely important. And the second bullet I would like to raise is that you don't have to consider duty cycle only at start of the design, because you need also to take into consideration if you do a firmware update of the sensor in an IT system, for example. If you update the firmware 1 year from now, would you still continue to keep the duty cycle of the system? Or is there risk that someone else comes in and breaks that duty cycle rule? That need to be covered already in advance so that you never break this. One thing that is very crucial, of course, in this discussion is whether the battery chemistry is suited for high peak currents. There are some very good battery chemistries that can run for many, many years, but they can't deliver that much peak power. A modem can, for example, run on a reservoir of power from a supercap or something, while the function X might run directly from the battery. And if function X then peaks with slightly above the power consumption or power capability of the battery, then function X will be the major problem in the system. So having said that, we continue into the system part. When you do system design of a low power system, you need to keep track of what is the core system functions and never, ever lose focus on those. When you do, and especially if you are many people working on this system design, there will be requirements that are mandatory and there will be desired or optional features. And when you look into these, there are, of course, also priorities among the mandatory things. It might be very easy to dig down into details of the desired or lower prioritized mandatory things, and they become more and more important over time. But in the end, you spend a lot of power on things that wasn't really the core functions of the system. So never ever lose focus on what the system core function are. Then when it talks to connectivity, and this is mostly regarding IoT systems, you need to understand how the installation, what it looked like. Is it an urban area? Is it long between base stations of a cellular system, or do you have access to a LAN? Do you have a network close by? Is there a LAN or a Wi-Fi that you can actually rely on? Companies and even private people, they change the SSID of the Wi-Fi, they change the PIN code of the Wi-Fi. Maybe they forget to inform you about this, or they forget about changing the PIN code in this IoT design. So you then lose the connection. If you go wireless, then you need to understand the markets, of course, of this design that you're doing. Should it be sold in the US? Should it be sold in Europe or Asia? So depending on what technology you use, there are different aspects of this frequency band registrations. There is also for IoT purpose something that is extremely critical. Connection interval is used as a nomenclature in both Bluetooth BLE as well as in IoT narrowband or narrowband IoT. This connection interval is very tightly connected to the duty cycle of the system. So how often are you connecting? How often are you connecting to the base station or a gateway or to the back end? And this might be a parameter that actually directly affects the selection of radio technology to use. If you're only allowed to connect once per day, there will be several technologies like Cat-M, cellular band Cat-M, which is not suitable for you. The required data rate and latency requirements, of course, makes a difference in selection. Connectivity distance I mentioned. If you are working on, say, 100 meters operating range between a gateway and a sensor node, most technologies like Bluetooth and Wi-Fi and other technologies are questioned, but BLE long range or coded PHY might be very suitable for you. On the other hand, then the data rate, peak data rate is reduced significantly. So that needs to be taken into consideration. One thing that is also very important is the system topology. If you look on a star network or a mesh network, I hope that you see my laser point right now. In the star topology, the sensor node, and let's right now focus on IoT. Each sensor node can wake up when it wants and connect to the central and then deliver the data that it should deliver and then go back to sleep again. And it only have to take care of its own power consumption related to its own function. If you look on the mesh topology instead, some of these sensor nodes might have to be routers in order to extend the distance, the operating distance. And a router node need to be, there are different technologies within the mesh system. You can be a flooded mesh where every message that you receive need to be transferred or sent out to the nodes that might hear you. Or you get a routing table that you know in advance that this message need to be routed to a sensor that within my reach or not. In any case, the router need to be running more or less continuously in order to receive messages to judge whether it should route it wide or not. And therefore, mesh topology is not that well suited for IoT systems if you have very, very low power sensors. Then you could argue for, yes, you could have a very low power sensor in the mesh network, and then the routers might be powered by mains or larger batteries, of course. If you now look into the hardware design, you need to identify the power consumers, and you should try to understand exactly what need to be always on. And it might not be the most obvious part. Typically, an RTC in an MCU, a small MCU, this could be embedded in a BLE transceiver, for example. You can power off the system so that it really is in the lowest possible power state, only running the embedded RTC. That's might be a good solution and might be a sufficient solution, but on the other hand, the embedded RTC might consume much more power compared to an external RTC. And an external RTC can be used to power on totally through a load switch, power on the MCU in total. So that consumes 0 until it's enabled. Split the design into different power domains, which is smart. And if you have a sensor node with multiple sensors, you might not have to monitor each sensor in the same frequency as any other sensors. Temperature, for example, is a slow changing thing, while there might be other sensors that need to be sampled much more often. And then they should be treated on different power domains, rather than keeping all the sensors running when sampling only one. And then you shouldn't forget about pull-up and pull-down resistors. And this is, for a hardware designer, this is well-known information. You all know this, but sometimes it's good to see an example. And I did a calculation here just to point out the really importance of this. A design will include several pull-ups or pull-down resistors, but if you take one only, 100K ohm pull-up resistor, and in the system where you have a 2.5 voltage system voltage, that will consume 62.5 microwatts for one resistor. If you calculate this over 1 year, that equals to 548 milliwatt hours. And that's even more than a CR2025 lithium-ion battery, a primary battery cell is, which has a capability of, or capacity of approximately 400 milliwatt hours. And this was only one pull-up resistor. Let's say that the firmware forgot to initialize all the GPIO pins in the correct way. Then you waste the whole battery capacity over a year from one single resistor. And as a good example of this, a poor example, first of all, would be a system controller that communicates with function X. It can enable function X by enable power to it. And when it's not used, function X can be disabled by disabling the power to this one. Communication in this case are to GPIO pins. If you have pull-up resistors connected to the system controller power domain, if you power off function X, you will have leakage through the protection diodes in the GPI pins on this function X, so that these pull-up resistors will actually drain in the range of 60 microwatts each continuously until the function X is powered on again. So the correct way of doing this would be, of course, to have the pull-up resistors pulled to the same voltage as the function X is. This might look very obvious, but we see in different designs over and over again that this is failing. This is done in the incorrect way. If you look into firmware design, one of the first important parts, and this is done in firmware and system study together, identify the best partitioning between IoT node, the gateway, and the cloud. For example, edge AI versus clouds AI need to be managed if you should do some artificial intelligence on this, or even simple calculations. How much processing is actually needed? And that is very important to understand whether you should do this processing on the edge or in the cloud. And of course, what is the power source? So assume that we are battery operated. The sensor is running on a small MCU. If you upload data once an hour so that you could monitor that and do AI processing in the cloud, that will consume power for the connection. Quite many connections over a 24-hour period. If you implement edge AI instead, you should sample the sensor and do your processing on the edge, and maybe upload the data once a day. So it's the connectivity power consumption is significantly less, but then you need to consider how much power is used during the processing of the data. if you just sample data and store it, there's nothing to it. But if you do a lot of mathematics calculations on this, then edge AI might not be the way to go. When you do photo updates, and every sensor today should implement firmware update over the air. This is supported by Bluetooth Low Energy, Bluetooth Classic, Wi-Fi, what have you. So photo need to be considered. And already when you systemize this, the device or the system, you need to understand how often you should do photo updates. And there are different reasons to do a photo update. One could be bug fixing, and by nature, that is quite common to have more bugs in the early days of a release. But there's another reason, that might be feature growth. So you might have a roadmap already from start saying that we will, in 2 months after release, we will update and you will get new features, and then you have a continuation of these updates. These should be scheduled because a photo update might consume a lot of power. Specifically, if you're running a system, maybe running a Linux, if you have a very small sensor, the firmware update might not take that much power. But this is something to consider. Then you need to identify the power consumers, of course. What IPs in the MCU or application processor and the power domains on the device can be powered off between activities. So most MCUs or application processors today offers quite good support to power off and stop the clocks for different domains in the MCU itself or application processor itself. You should, of course, not spend a lot of power on clocking a GPU, a graphical processor, if you don't use that. You shouldn't even clock a UART block if you don't use that. So each and every small block that you can stop the clock to will save power. Then you should go to the lowest possible sleep mode as soon as possible. Most MCUs and application processors will support a variety of sleep modes, and the difference between those might be wake-up sources. Typically, can you wake up on an interrupt on a GPIO pin, or could you wake up on a watchdog timer, or can you wake up on the RTC? So you need to select the one that is most appropriate for your system. In the example that I brought up, using an external RTC rather than an internal RTC, then you might not even have to bother about the low power modes. You just turn everything off. But if you would like to run on the internal RTC, then the lowest possible power mode with RTC wake up resource should be selected. Another thing that makes a big difference over time, if you look over a year or many years of operation, that is the accuracy of the RTC oscillator. If you look for example, on Bluetooth, you have a paging interval. Each and every device needs to listen for a paging and listen whether it's getting paged or not. And if it's not paged, then you can go back to sleep again until you need to wake up for next paging interval. If you need to wake up way in advance to make sure that you're absolutely powered and running when the paging time comes, of course that will consume more power. And that is the case when you have a more accurate clock. You can't rely on the frequency exactly, so that you need to have some kind of guard time before. So you make sure that you're alive when the paging occurs. The same goes for Wi-Fi. So a more accurate clock will actually make a huge difference over time. Schedule events based on RTC timers or any other hardware timer as much as possible. I think the RTC timer is super efficient when you talk about IoT systems, because in many IoT systems you're monitoring some very slow activity. Could be temperature monitoring, could be moisture, could be whatever, and you shouldn't have a software timer running to wake up and do things on that slow period of time. So keep RTC timers running and try to power off as much as possible. So low power state versus data retention. This is more active when you talk about a Linux system or an Android system where hibernation mode is possible. For some systems, the booting will consume a lot of power. Typically, a Linux system or Android that consumes quite much power when you boot. And then when you're up and running after a lot of time, because it takes many seconds to boot a Linux or an Android system, then you can start being active. If you can go into hibernation mode instead, storing the register states in RAM and keep the DRAMs in self-refresh and power off power to the CPU and the cores and everything else, then you will save a lot of power compared to having the system running on low power mode. But this is typically for systems where hibernation is possible. This is, I would say, not realistic for state machines or real-time OSs. And then this is going back to the thing that we covered in the hardware session. Do not forget about GPIO pins. And the GPIO pins will result in power consumption. So if you turn off function X, make sure that you have no GPIO pin that is active logic high that will back power that function X through the GPIO pin and the protection diodes in that port. So it makes a very big difference, and especially over years of operation, it makes a significant contribution to the overall power consumption. Now, these states will change depending on whether you enable a function or not. So if you enable function X, you need to define the GPIO pins in one way. And then when you power off that function, you should, of course, not forget to reset all these pins and interfaces that you have in that. Now I will, this is actually a good summary, a case study where most of the stuff that I've covered here will be covered. This is a case study that I can't reveal the application. It's something that we do for a customer right now. What I can tell you is that it's a wireless sensor node system. Each IT sensor are self-powered or is self-powered. The function of the system is that the sensors should report sporadic events when they occur, if they occur. And if they don't occur, at least once per 24 hours, we should connect to the gateway to do a housekeeping. Keep alive information, sharing whatever events that happened during the day if something were missed, and also just possibility to do food updates. Each sensor node need to live for 20 plus years of maintenance-free operation. The thing is that it costs tremendous amount of effort and cost to go to these sensors and repair them or maintain them. So they need to be maintenance-free for 20 plus years. The system topology is star network, or you could argue for point-to-point. The amount of data to send is approximately 24 bytes upon each event. And then, as I mentioned, once per day, you have a scheduled housekeeping where you share approximately 24 bytes. The operating distance is up to 100 meters, but there are some sensors would be closer. And the quality of service is best effort within 30 seconds from the event. The power source, as I mentioned, is self-powered. They are running on battery, but we did, during this early part of this study, look into energy harvesting, and we will come back to this. Taking all this into consideration, especially the number of bytes to transfer, the operating distance, the star topology, and the power consumption, we concluded that BLE long range would be suitable. And this is the coded 5 version with a really lowest possible bitrate, 125 kilobits per second. Narrowband IoT was also considered, and we'll come back to that. One reason in this early study why it was put into parentheses was that its narrowband IoT was not covered in the markets by all operators. It is still not 100% covered in all markets, but I will come back to that. Other functions or circuitry in this sensor node is that we have a passive detection circuitry that will detect the event that the whole idea is to monitor. And this passive detector will consume approximately 3 microwatts. The external RTC is used because that consumes in the range of 30 or 300 nanoamps compared to maybe at least 3 times more if you use the embedded RTC in the BLE long range transceiver. So an extremely low power RTC was selected. And then everything else is powered off. So the only thing that is running is the RTC and the detection, passive detection circuitry. I'll try to guide you through this slide. You don't need to look into the details. This is BLE long range power estimations. We do advertising with a 1 second advertising interval. It means that we transmit an advertising package on the 3 advertising channels every second. And then we actually power off the system in total. 10 milliwatts is consumed in average over this advertising session, and then you go back to 3 microwatts when everything is powered off. And then you wake up again after 1 second and you transmit again. The mean power consumption over this 1 second is 403 microwatts. If you now consider a system running without any events whatsoever happening, you only have the housekeeping that is happening once per 24 hours. That housekeeping will consume approximately 403 microwatts during a period of 120 seconds. And then for the rest of the 24 hours, you only consume the 3 microwatts. That again came from the RTC and the passive detection circuitry. The mean power or average power consumption during 24 hours is now approximately 3.6 microwatts. If you now take into consideration the worst case where a lot of events is actually happening, we concluded together with the customer that one realistic worst case scenario would be that we have one event every 10 minutes over a period of 2 hours, and then there is nothing more. So then we have a 304 microwatts consumption during the housekeeping, and then we are doing 3.6 microwatts power consumption during the events. And then for the rest of the period, there is only the 3 microwatts. Now, we keep these numbers in mind. And then we have the same example for narrowband IoT. And there is a small, for those knowing details of narrowband IoT, this is the active session where transmission and receptions. But when we go into transmission, you have approximately 700 milliwatts power consumption, but the reception is significantly lower, 66 milliwatts. But if this session is going on for 10 seconds, the average power is then 198 milliwatts. This is for 10 seconds. If you now do nothing else than doing the housekeeping transmissions once during 24 hours, the mean power consumption is 26 microwatts. If you now do the same worst case scenario, again, 10 minutes, one event per 10 minutes over 2 hours range, and then the rest of the 24-hour period is nothing, then the mean power consumption over 24 hours would be approximately 300 microwatts. So if we go back and compare 3.6 microwatts to 300 microwatts, you see that there is a significant difference. On the other hand, when you look into the system design and selecting what technology to use, it might not be possible to do anything else than cellular connectivity. Thus, narrowband IoT might have been the obvious selection. In this case, for this application, we actually have a gateway in close proximity that monitors multiples of these sensors, and that gateway in itself can be connected to the backend over some cellular network. So, for this specific application, narrowband IoT was not the obvious choice. When we went into the power solution analysis, we of course looked at energy harvesting, because this is a device that actually moves. And the motion results in vibrations in 2 dimensions. So we have up to 1 G vibrations in 2 dimensions. The frequency of these vibrations are in the range of 5 to 200 hertz, which is actually very suitable for some vibration energy harvesting. We also looked into RF energy harvesting. And the reason for not selecting that one is that the energy that you could harvest was not enough. And RF energy harvesting could be done in several ways. You can, for example, look for a cellular network and probing power from that. You can look for television or radio transmissions on other frequency bands. But the power wasn't enough. The solution that we looked more into was actually having one dedicated transmitter, our energy transmitter, that pointed its energy towards each sensor. But the distance of 100 meters made it impossible to harvest enough power. So RF energy harvesting was out of the scope. So was solar and temperature, and this is due to the application itself. Now, looking more into the vibration energy harvesting, there are 2 typical ways to harvest vibrations. One is the electromechanical solution. One company called Revive have solutions where they can deliver up to 1 milliwatts per 0.25 G. The piezo actuator is another technology. Typically, MIDE is a company that delivers these. They can deliver up to 2 to 5 milliwatts even at 0.5 G. But the problem and the difference between these 2 is that the electric and mechanical harvester, what you see in the upper part of the picture, these are typically voice coils. You have a magnet, a permanent magnet that goes up and down inside a coil. And it's loaded by a spring, so that it becomes resonant, but it's slightly wider in the frequency range of resonance compared to the piezo harvester, which are like fingers that you can tune to a certain resonance frequency by the finger length and a weight that you can attach on the tip of the finger. You can see this weight on this MIDE resonator, meaning that the piezo actuator needed to be tuned to a certain frequency, and for this application, we needed to cope with a range of frequencies between 5 to 200 hertz. But again, this is good information to many of you that vibration energy harvesting is actually resulting in quite big power. We also, of course, looked into the primary battery cell. And there is a very interesting chemistry called lithium thionyl chloride. One of the advantages with this technology is that it works in a very wide temperature range. So minus 55 to plus 85 degrees Celsius. Now I'm talking about one battery vendor. There are numerous vendors that offers these battery chemistries, but Taderon is one company that we have been working with. This example, this specific model is like 33 millimeter in diameter, which is this one. I hope that you see it in the bottom right corner. It offers a capacity of 5.5 watt hours. And one of the disadvantages with this technology or chemistry is that it can't provide very high peak power. So typically 0.5 milliamps, but you could have a max continuous discharge of 10 milliamps. On the other hand, what we came to conclude during the work was that in the very cold temperature, like closer to 40, you actually build up a very high internal resistance in the battery, which reduces the possibility to draw high peak currents. And this was another aspect or another reason not to use the narrowband IoT, because we couldn't source enough power to that. If you now look on the power numbers that we calculated or I shared with you regarding narrowband IoT and the Bluetooth Low Energy, the conclusion was that narrowband IT could last for approximately 2 years. But this is purely on the capacity of the battery and the consumed energy by the system if we would have used narrowband IT. The conclusion that I mentioned, that the power delivery capacity was less in cold temperature, makes narrowband IT less useful, and 2 years is questionable. But the very low power consumption of BLE long range actually, on pure mathematics, would work for 174 years. Of course, this is not true because the battery leakage is the limitation itself. But it shows that we have a huge margin between the capacity of the battery and the energy consumed by the application. So we concluded that we should be able to use the lithium thionyl chloride battery for this application. And I think that concludes the webinar. What I would like to, I hope that you can bring this with you, that the duty cycle of a system is extremely important of how well you can run this system on batteries for a long time. 20+ years is realistic for BLE long range, as shown by this case study. Thank you with that. I think, Lars, should we do a Q&A session?
Yeah, we can most definitely do a Q&A session. However, it seems that the presentation speaks for itself because there are no questions posted as of right now. So for all the attendees that have listened, if you have questions, please take this opportunity to write them in the Q&A functionality of the webinar. And in the meantime, while we are waiting for the questions, and maybe there will not come any, for the ones of you that have a QR code reader on your phones, I suggest take that up, and you would then be transferred into a survey that we would like kindly ask for you to reply upon in order for us to become better in the future. I got the question here that actually is whether or not there will be a follow-up on a second part of this webinar, and most definitely there will. There will be on April 28th. We are planning for the second. No, now I'm mixing the dates. On 28th of April, we will have a Tech Tuesday hosted by our colleague Carl Fredrik Kastenge. And there will be more information to come on that. But the second part of this low power system design will be on the 8th of May. Exact time we will come back with through social media and our normal communication channels.
Yeah, I can mention as a teaser for that system, we will go into graphical systems and things to consider when you have a graphical UI on your device.
Great. I am currently not seeing any more questions or question marks. If you don't manage to get the link to the survey right now, it's not a problem. It's going to come through email in a day. If there is nothing more that you would like to add on, Håkan, or possibly you, Hamid, I suggest then we close the webinar. Thank you for today's session and enjoy your weekend, everyone.